We present Pathways on the Image Manifold, Image Editing via Video Generation. The goal of image editing is to alter an input image, usually guided by a target image or prompt. In recent years, there have been significant advancements in this area, driven by the rise of diffusion models. This process can involve object replacement, background modification, non-rigid transformations, scene relighting, and many more tasks. Image editing presents a core trade-off: edit accuracy versus preservation of the original image content. For example, when editing a tennis ball into a tomato, we want the output to clearly show a tomato, while preserving the original background and scene composition. Similarly, when editing a giraffe to appear as if it's eating grass, we want it to crouch realistically while maintaining its original characteristics, such as shape, texture, and style. We explore editing on the natural image manifold. To enable this, we simulate the manifold using synthetically generated data. We generate portraits of people with AI printed on their shirts, portraits of people making heart shapes with their hands, and a final group combining both, wearing AI shirts and performing heart shapes. We then take all the images, add a set of pure noise images, and perform dimensionality reduction. This is done by encoding each image using a clip image encoder, followed by applying PCA to the output embeddings. The projected 2D embeddings form a smooth manifold, clearly separated from noise. Within this space, we observe a semantic progression, from AI shirts to AI combined with heart shapes to heart shapes alone. Given an input image of a person with AI on their shirt, we aim to edit the image so the person makes a heart shape with their hands. Current editing solutions perform what we call single-stage edits, producing only a single output image. As illustrated, this can cause an abrupt transition, jumping directly to the red cluster and removing the AI on the shirt, resulting in a loss of consistency with the source image. This contrasts with the desired outcome, landing in the purple cluster, where the person performs a heart shape while still wearing the AI shirt, preserving the original image content. To avoid such abrupt transitions, we aim to move progressively along the manifold, creating a smooth path that incrementally applies the edit while preserving the source image's characteristics. We achieve this by leveraging video generation. Video generators have advanced remarkably this year. Many view them as world simulators, models capable of capturing physical dynamics while maintaining temporal coherence. Put simply, these diffusion-based models start with pure noise frames and gradually denoise them into a coherent video, guided by an input textual prompt. Their image-to-video variants are additionally conditioned on a starting frame, guiding the generation to remain consistent with the input image. In this work, we explore how image-to-video models can be leveraged for image editing, enabling smooth traversal across the image manifold to achieve gradual, content-preserving transformations. An editing task typically consists of an input image and a caption describing the desired target image after the edit. Unlike the typical setup, our approach fundamentally differs by modeling editing as a temporal process. This requires a new type of prompt, a temporal editing caption, which describes the sequential transformation from source target. This caption effectively serves as a set of navigation commands along the manifold. In addition, the output is not a single edited image, but a sequence of frames. The optimal number of frames required can vary, and the last frame is not necessarily the best result. Later frames often drift further from the original image. Therefore, we select the earliest frame that satisfies the edit request. This combined pipeline of temporal caption composition, video generation, and frame selection forms the basis of our method, dubbed frame-to-frame. Ablation studies demonstrating the effectiveness of each component can be found in our paper. To avoid manual intervention, we demonstrate that the entire pipeline can be automated with the help of a vision language model. The temporal caption is generated by providing the model with the input image, target prompt, and a set of instructions and examples. For frame selection, we convert the video into a grid-based image representation and feed it to the model along with the target caption and relevant instructions. Here are examples showing how the model can produce different edit pathways for the same edit request. The tomato replaces the tennis ball in multiple ways, landing from above, being swapped in by a hand, through various warping transformations. We compare our model with leading image editing methods on the TED-Bench dataset, highlighting its superior performance across diverse editing scenarios. These findings are further supported by quantitative comparisons, including both model-based metrics and a human evaluation study. We also propose pose edit, a new benchmark for human pose editing. Our method achieves more accurate pose changes while preserving identity and consistency. In addition, we demonstrate the versatility of our framework by applying it to fundamental image manipulation tasks, denoising, deblurring, outpainting, and relighting. We believe this highlights frame-to-frame's strong potential for a wide range of image manipulation applications. Thank you for your time. To learn more, please visit our project page.